Hi, everyone. My name is Derek Davis. I'm an assistant professor at the University of Rhode Island. And on behalf of the LIGO Virgo Cogger collaboration, I'm excited to welcome you to the first in a series of webinars detailing new results we've shared as part of the fourth update to the Gravitational Wave Transient Catalog, which we refer to as GWTC. Today's webinar is going to be focusing on introducing everyone to this catalog and discussing the open data associated with this new release. However, please make sure you pay attention to your email inboxes and on social media, as over the next few weeks and months, we'll be having additional webinars focusing on the wide range of scientific methods and exciting astrophysics we've been able to learn from this catalog, including how we identify gravitational wave signals, estimate their properties, understand the broader population of sources, and even look for evidence of new physics. So without further ado, I would like to introduce Greg Ashton from Royal Holloway, who's going to be guiding us through the rest of the webinar today.
Thanks very much, Derek. Very much appreciated, and welcome to everyone to this webinar. So let's get ourselves going through. Just as a notice, so as Derek has already mentioned, this is going to be focusing on two papers from a series of papers: the GWTC 4 introduction and the open data paper. And so we'll get to those in turn, but as Derek mentioned, there is also sort of methods and results. So in other words, don't expect too many results from today. We're mainly talking about the infrastructure, the instruments, etc. So let me then introduce my fellow panelists and what they're going to be talking about. So firstly, we have Elena Capote from LIGO Hanford, and she's going to be talking about observatory evolution. Then we have Agata Trovato from the University of Trieste, who will be telling us about the interferometric strain data. And then finally, Matthew Dubois from L2IT, I'm never sure quite how to say that, who will be our expert on the electronic catalog. This is their expertise, so a wide range of things here. Myself, I work mainly on data analysis, Elena on the detector itself, Agata on both data analysis and also GWOSC, which we'll be introducing, and then Matthew on GWOSC as well. Okay, so why don't we get into our webinar here. So I'm kicking us off by trying to tell you a little bit about what the gravitational wave transient catalog is. Before I do that, I just want to remind everyone that we're, a collaboration of multiple different instruments spread across the globe. So we have our two lovely LIGO sites, Hanford and Livingston. We have the Virgo site in Italy, and then Kagra also in Japan. So this is a really global network of gravitational wave observatories. And these observatories, as I'm sure many of you know, are running and taking data in coordinated observing runs. So this is, I think, one of the most fascinating features of astronomy. In fact, as a gravitational wave astronomy, as opposed to astronomy, is we are sort of banded together because we get so much more out of our instruments when they're operating together, as opposed to sort of pitted against one another. So in the bottom here, I'm showing the timeline of different past observing runs and future observing runs. And you can find more details about that at that link, observingdocs.ligo.org. And so what you see is that these the instruments have been sort of slowly increasing in sensitivity. So the little numbers above each of the bands, that's giving you this metric, the BNS distance. So the distance you could roughly see a BNS to, and you can see that that's increasing. We sort of doubled it from 01 into 04. And we're also taking longer sections of data. So currently we're in the end of 2025, and 04 is still ongoing. And so we've been taking data now since 2023. So this has been the longest observing run to date and the most sensitive, and has included many periods of 4 detector data as well. So, okay, so let me finally get then to what the gravitational wave transient catalog is. So the 3 collaborations, LIGO, Virgo, and Kagra, release their strain data in bulk at the end of sections of each observing run. And so in August 2025, the first part of the 4th observing run, so O4A, the data from that was released. Matthew will be telling us more about that later on. But in addition, they also release a gravitational wave transient catalog, which is containing information about all of the transient signals that we've discovered in the data. Um, to date, all of these appear to arise from mergers of compact objects, so black holes and neutron stars. And it contains both the results of searches for those signals and then also parameter estimation as well. And if you like, it's the sort of raw data product that is used by many of the downstream analyses to do sort of some of the things that Derek was talking about earlier on, like constraining the cosmological evolution of the universe, etc. The thing I'll add here is on the right, we have a little plot which is taken from the GWTC 4 introduction paper, and it gives you a sort of another view of the timeline that we have on our observing page. So what you see is with almost the same colors, each of the observing runs now sort of sketched out, and then little black lines, if you can see my cursor there, indicate each of the detections that we've made. And what you'll notice is these horizontal lines indicate each of the catalogs. So GWTC1 included data from O1 and O2. GWTC2 then covered data up to the end of O3A. There was then also a GWTC 2.1 that covered the same period, a GWTC 3 that went up to the end of O3B, and now GWTC 4 includes data up to the end of O4A. So each of these data sets is cumulative in the sense that we consider GWTC 4 to contain all of the events from O1 through to O4. Okay, so then one final view of that data, which is now we're plotting it instead of in linear time, we're now showing it as a function of the cumulative effective hypervolume, which is in some sense the time distance volume that we have surveyed as we've operated our detectors. And so I think what really clear from this is that the improvement in sensitivity and longer duration of O4 means that just O4A alone is larger than all of the sort of hypervolume that we had seen beforehand. And so that took us from almost 100 or so detections up to over 200. And this is a sort of rough metric based on the sensitivity. So you'll hear more about the specifics of those detections in our methods and results webinar that will be coming up, but this is a little bit of a taster of it. So, okay, so what I guess is this webinar sort of, what is this an introduction to, if you like? Well, something that we're doing differently compared to previous releases of the gravitational wave transient catalog is rather than releasing a set of papers all together, which are loosely coupled together, we're now working tightly with the Astrophysical Journal to produce a focus issue, which is going to be targeted just on all of the papers which are related to GWTC 4.0. So currently, most of those papers are under review in the Astrophysical Journal. And the focus issue is going to come out once they have passed through peer review. A couple of advantages of this focus issue. So it enables us to clearly group together papers and tightly coordinate them. So that will reduce sort of the duplication between different papers. And ultimately, what we're looking for is to make these papers easier to read and easier for people to find the important details that they want to find. And then on the right-hand side, what I have is a sort of list of a couple of the papers. So the two highlighted in blue are the two that we're going to be talking about today. So the first is the open data paper, which is, of course, the paper which introduces the details of the data that we're publishing and also the details of the electronic catalog. So we'll actually get to that in the last two speakers of today. And then the part that myself and Elena will be talking about is the paper GWTC4, an introduction to version 4.0 of the gravitational wave transient catalog, which is the sort of opener, if you like, for the whole focus issue. As I say, there's methods papers and results papers as well that are targeted just on the catalog, and then there are a series of other papers as well that many of which are on archive And I've put the link there to our main page where you can find all of those. So I'll just say briefly, in terms of the introduction, it is just an introduction, but it's the idea is to give an overview of the entire focus issue. It includes some performance metrics and timelines, and it serves as a reference manual. So, for example, if you want to know how we name our catalogs and how we name our events, that's sort of detailed there. In some cases, sort of for the first time, some of the specifics. There's also a nice review of observed transient sources, which includes sort of tables introducing, standard names. And the idea is therefore other papers in the focus issue all use exactly the same nomenclature, and we try to improve consistency between our papers. And then there's also appendices, which introduce sort of acronyms and glossaries, and then conventions for data analysis. So I guess I can advocate for this paper, especially if you're a beginning PhD student, or maybe you have research students that are starting on this topic. I think it serves as a really great sort of overview of many different parts of the field. The other part about it, which is also really nice and something that we haven't done in the same way that we have here, so it's, I think, exciting to introduce, is that we have an historical overview of the observing runs and the instruments. And with that, I can pass over to Elena, who's going to actually be the expert in the room for the instrumentation.
Fantastic. Thank you so much, Greg. So yes, hello, everyone. My name is Elena Capote, and I'm going to talk about observatory evolution. So we can go right away to the next slide. Because both LIGO detectors were the main detectors observing during O4A, I will focus on the upgrades for the LIGO detectors, and following catalogs can also continue information about the upgrades to the Virgo and Cagra detectors. So the LIGO detectors can be detailed as enhanced Michelson interferometers. And a goal is to detect a gravitational wave signal by leveraging the coupling of a gravitational wave to a differential arm length change. So it's sort of in the middle of this page, you can see a cartoon schematic of what the LIGO detectors look like. And you can see at the heart of this layout is a beam splitter. So this sits the heart of our Michelson interferometer. Each of our arm cavities are 4 kilometers long, and they are designed to be Fabry-Perot arm cavities. So we can further amplify the laser beam resonating within the cavities and amplify our sensitivity to gravitational wave signals. And this has been the basic layout since the beginning of the first observing run. Other elements that have been there since the beginning include power and signal recycling cavities at the input and output of the detector. You can see them labeled here on the plot. These cavities serve to amplify the laser power that goes into the arms in terms of power recycling. So this again amplifies our sensitivity to gravitational wave signals through adding additional resonance components to our system. And then our signal recycling cavities at the output of the detector serve to broaden the range of frequencies of gravitational waves that we are sensitive to by broadening the detector bandwidth. Additionally, because we continue to add so many cavities to the system, we also have things like input and output mode cleaners. The input and output mode cleaners are designed to clean the spatial mode, hence the name mode cleaner, so that the beam going into the arms, and for example, in the input mode cleaner is a very nice round, what we call Gaussian TEM00 mode. And for our output mode cleaner, that cavity serves to do the same thing so that the beam that makes it to our detection port similarly is a nice TEM00 mode. We also use those cavities to help filter out excess noises that might couple, such as laser noises or other noises from other optical fields in the interferometer. And so, as I said, this has been a pretty standard layout of our interferometers since the beginning of our gravitational wave astronomy in O1. However, there's a very notable upgrade to both LIGO detectors for observing run 4, which is the 300-meter filter cavity that's sort of the bottom right of this diagram. And the goal of installing, thank you, the goal of installing this 300-meter filter cavity is to improve our quantum limited sensitivity of our detector through the implementation of something called frequency dependent squeezing. So let me tell you a little bit about that, because I think it's a really exciting upgrade to our detector. Back in observing run 3, the detectors performed squeezing as well to improve their quantum limited sensitivity. And the goal of squeezing is to reduce quantum noise that's present in the detector. At high frequency, we are limited by quantum shot noise. And you can think of shot noise as a noise that arises from the uncertainty and arrival time of photons on your detector. And this is something that we can also think of as an uncertainty in the phase of our light. Meanwhile, we can be limited at low frequency by radiation pressure noise, which we can think of as an amplitude uncertainty of our light. Amplitude and phase uncertainty act sort of in the same sense of the Heisenberg uncertainty principle. You can envision this as if you have the product of your amplitude and phase uncertainty has a minimum value that is not zero. And so you can imagine, we often think of it as a circle. When you have equivalent phase and amplitude uncertainty in both quadratures, you've created some sort of circle in this amplitude phase space. However, quantum squeezing allows us to play with the Heisenberg uncertainty principle by minimizing our uncertainty in one quadrature so we can leverage the sensitivity improvement. So for example, in observing run 3, we performed frequency independent squeezing, where we only squeezed in the phase quadrature, reducing our uncertainty in the phase quadrature and therefore improving our high frequency sensitivity very significantly. However, as you do that, you then make a sacrifice. You start worsening your sensitivity in the other quadrature and increasing noise, perhaps at low frequency due to radiation pressure. So the beauty of frequency dependent squeezing, it allows us to have both of those things at the same time. And so the graphic all the way over on the right, the bottom part of that graphic is demonstrating for you such what the frequency independent squeezing might look like. You have minimized your uncertainty in one quadrature. So you have this ellipse, and it's the same ellipse over a range of frequencies from 10 to 100 hertz. However, frequency-dependent squeezing and the implementation of a filter cavity allows you to rotate the angle of your squeezing. So at low frequency, you can perform an amplitude uncertainty minimization, where at high frequency, you can perform a phase uncertainty minimization. And therefore, you're able to improve your sensitivity broadband in your detector. This is a really fantastic upgrade that we added to both LIGO detectors that has led to alone a significant sensitivity improvement. In addition to the filter cavity, it involved the installation of several new optics and vacuum volumes so that we could steer the squeeze beam into the interferometer so it could interact with our main laser beam. So that was one of our most significant upgrades for observing run 4. We also sought to improve our quantum limited sensitivity by improving our intracavity power. So the arm power that resonates in our X and Y arm cavities, we continue to increase that because that's another way to improve our shot noise limited sensitivity. In order to do that, you have to be able to deliver more power to vacuum. So another place where we did upgrades for observing run 4 was at our pre-stabilized laser. That's the component right at the beginning of our system. We had to be able to deliver more power to vacuum. So we implemented new amplification stages and improved laser components so we could deliver higher power. For observing run 4, the LIGO detectors at Hanford and Livingston operated between 55 and 75 watts of input power, resulting in 280 to 360 kilowatts of resonating power within our arm cavities. One of the challenges in previous observing runs was also the presence of point defects. So the mirrors that serve as the mirrors in our Fabry Pro arm cavities are reflecting a large amount of power, and any small point defect on those mirrors can cause wavefront distortions. Small point defects might absorb excess power than we expect. So we move away from uniform absorption and end up with some strange optical field that's being reflected off our mirrors. By replacing several mirrors at both Hanford and Livingston, we were able to install mirrors that had no such point defects. And this enabled us to operate at higher and higher powers, also reduces optical losses for us and makes our controls a lot simpler because our optical fields are not getting distorted. We also underwent a huge effort to reduce noise from scattered light. This involved trying to reduce motion of things like baffles that might reflect stray light back into our main interferometer beam. We also removed a window at the output port between our output Faraday isolator and our output mode cleaner. And that window was a site of a lot of acoustic noise coupling because it just picked up any sort of ground motion and coupled it into our system. And finally, there was a huge effort at both sites to improve noise from controls. Technical noises like controls noise can significantly impact interferometer sensitivity at low frequency. So this is below 100 hertz. We were able to reduce link controls noise by a factor of 2 at both detectors and angular controls noise by a factor of 10. And so you'll notice that the low frequency sensitivity in observing run 3 was significantly limited by these noise sources, and it is no longer so limited. And so that is one of the reasons why our low frequency sensitivity has improved. So let's actually take a look at what that looks like. Greg, if you'll advance the next slide. So here we have plotted our gravitational wave sensitivity in the frequency domain. So we take our gravitational wave signal, which is calculated via the differential arm length change of our two arm cavities, as I demonstrated on the previous slide. And we convert that into the frequency domain via a Fourier transform and calculating a power spectral density. What I'm showing you here is the amplitude spectral density. So we've taken a square root of that power spectral density, and this is in strain units. Strain is a unitless quantity. This is a delta L, change in length, over the total length L of our arm cavity. So the y-axis there is showing you strain units in 1 per root hertz. This is a spectral density, hence that per root hertz unit. Our x-axis is showing you the frequency, and you can see the band over which our detectors are sensitive, from roughly 10 hertz to a few thousand hertz. And these plot is nice because it's showing you the evolution of our sensitivity from observing run 1 all the way through observing run 4, which is the nice bright red and blue colors here for LHO, LIGO Hanford Observatory, and LLO, LIGO Livingston Observatory. And so you can see that both detectors have improved their sensitivity all across the frequency band. The high frequency improvements, such as the ones around 1,000 hertz, can be traced mostly to those improvements in quantum squeezing that I mentioned. We were able to reduce our shot noise via the improved power operation and our improved squeezing. At mid-frequency and low frequency, there are some improvements from quantum squeezing. For example, at low frequency, we've been able to maintain our sensitivity by keeping our radiation pressure noise reduced. But at low frequency, you can also see that we have reduced a lot of the noise, and that mostly comes from our reduction of controls noise. And there's other spectral features and artifacts that have been removed. Some of those come from things like reduction of scattered light noise. Another way to consider our detector performance is to look at the duty cycle of our detectors. We considered the duty cycle sort of as a measure of how much time we are in observing. The observing percentage for a Hanford detector was about 67.5%, and the Livingston detector about 69%. If you compare these numbers to O3b, or just our previous observing run, you'll see that these numbers are a little bit lower. And that is due to a few challenges that both detectors face, especially early on in the run. I mentioned that controls are a significant issue for us in noise. They can also impact our stability, and Hanford in particular at the early part of the run struggled to maintain control stability. And so we had frequent times where we would go out of observing due to a lock loss. In other words, we're losing the resonance condition in our cavities. Luckily, we were able to do commissioning that helped us overcome some of these control challenges and maintain a much more stable operating point. Livingston was also impacted and had frequent lock losses at the start of the run, but this was actually related to logging that was near the site. They actually came to chop down trees very close to the detector, and that is a very, very noisy process. And unfortunately, noise from environment can really impact our ability to observe. So luckily, both detectors were able to overcome these early challenges, and I think get a pretty good duty cycle towards as the O4A progressed. This led to a double interferometer coincidence of about 53%. We can go to the next slide and look at another way that we can quantify our detector performance, which Greg has briefly mentioned, which is via astrophysical range. Our standard range metric we refer to as our binary neutron star in spiral range. And this is the sort of the average range we could roughly measure a 1.4 solar mass binary system. We usually think of this as measuring it with a signal to noise ratio of 8. This low mass system provides a really good metric because the lower mass means that you will detect over more frequency. So this gives us a really nice broadband view of our sensitivity. However, we know that higher mass sources can be detected at further distances. So you can see here on the first plot on this page, the x-axis is showing you the time from the 24th of May, 2023, when we began our observing run through the end of O4A. And the y-axis is showing you binary neutron star range. And I'll note that the y-axis starts at 60. So we cut off sort of the lower part of the y-axis. So you could zoom in and see that the LIGO Hanford and LIGO Livingston detectors had sensitivity that ranged roughly between 140 to 160 megaparsecs. So these would be the distances to which we could observe this binary neutron star merger. The Hanford detector started out at a slightly lower range, again, related to these control challenges that I previously mentioned. But as you can see, the range improved, and even the Livingston detector range improved. This is because we were allotted a little bit of commissioning time that we were able to use to continue to improve the controls or other noises in the detector and improve the sensitivities. This roughly was a few hours a week that we really leveraged as much as possible to our advantage to make our detectors perform as well as possible. In terms of the distribution of our sensitivity, you can actually see in the right-hand plot, now the x-axis is our binary neutron star range, that the Hanford sensitivity is actually sort of bimodal with an average sensitivity of around 148 megaparsecs, but the sort of the higher peak is near 157 megaparsecs, so the lower peak is near 140. So that 140 portion corresponds to early in the run, and 157 to later in the run. Livingston is on average around 156, but you can see there's a small bump as they continue to improve up towards 160. So overall, we are really excited about the performance of these detectors, and we think that this fantastic improvement in sensitivity has been a key factor in the exciting results that this catalog is presenting. I'll hand it off to the next presenter now.
So, hi, I am Agata Trovato from Trieste, and I will talk you about the strain data. So, go to the next slide, Greg, please. So as it was discussed before, the interferometer is a complex instrument, is an interferometer. So the readout, the final information we have is the signal, the readout of the electronic, the photo, the light that we get at the end. We need to convert this readout, so this electric thing, in a gravitational strain equivalent time series. And this is done with a procedure that is called calibration. And basically, it's based on a model of the detector that is used to get from the interferometer signal to the strain data. This procedure is quite complex, and 404A was done mostly, basically, the final calibration was done online. And in addition with the calibration, we also have an estimate of the uncertainty that is associated with it. And in this slide, you see plots that are present in the open data paper that show the calibration uncertainties for living for the two LIGO detectors. So Hanford is in red and Livingstone is in blue. And you see 4 plots because the upper plots refer to the magnitude of the calibration error, and the lower plots refer to the phase of the calibration error. So if you imagine the strain data as the typical sinusoidal, you can be wrong in the maximum of the sinusoid, also in the phase. And you see the colorful bar show the median of the calibration error, and the band show the 1 sigma uncertainty. And the x-axis is the frequency. And I make you notice one important thing. This plot goes from 10 to 5,000 Hertz. So data outside this range are not calibrated and should not be used. So in general, you see that the calibration error is always less, since you see the extremes of the y-axis of the plots are always below 10 degrees in percentage in the magnitude that you see in the upper plot, and 10 degrees in phase that you see in the lower plot. The black dots that you see are some specific measurement that are done at very specific frequencies to check that the calibration procedure is done correctly. So there is a photon calibrator that moves the mirror to check what is the output and verify that our model is correctly used. Okay, you can go to the next slide. Besides the calibration, another important concept to understand our data is the quality of the data. So we assume that the data, in many analysis, we assume that the data that are stationary and Gaussian, but actually in real data, there are some disturbances of many time that affect what is called the quality of the data. We can roughly say that the two categories of kind of disturbances that we can define are what are called lines. So some persistent artifacts that are usually always there, but or at least slowly time varying, but usually at specific frequencies. And you saw that lines already in the plot that was shown by Elena a couple of slides ago, where she showed the sensitivity. There were vertical lines, and these were the line I'm talking about. And these lines are caused by many things, by the main line of the electric system. Also the calibration I was mentioning before creates some line, but also many other things in the detector. Another kind of noise that is present in the detector is what is called glitch. So this is the opposite conceptually of the line, is short duration in time, but can have a frequency evolution. And also this can be related to really many different sources, for example, from the environment, but also from the detector itself. And another important concept that I will mention that is important to understand our data is the hardware injection, which I have already basically mentioned. As I said, in some cases, so if we have to understand the detector, we use a photon calibrator to move the mirrors and mimic the signal of a gravitational wave. This is done for many reasons. Could be done for estimate the quality of the data to understand the couplings within, for example, our auxiliary channel and the strain data, but it can be also done for activities that has to do with the various kind of searches that we have in our data analysis. And okay, yes, you can go to the next slide. In addition to all this, we identify some data quality flags that are used to identify which are the periods that can be affected by some data quality issues. Usually we use this label cut 1, 2, and 3. And the order is in order of severity. So cut 1 is the worst that can happen, and then cut 2 and cut 3 is a little less important. And we use in the data this category to identify periods in which this category of data quality are passed, so that are not there. So and all the data that we release pass this cut 1 flag. So there are no critical issue, critical problem in this data. Okay, we can go to the next slide. So where you find the data in the Gravitational Wave Open Science Center, and you see a screenshot besides the link of the website, in particular about the O4A data release. You find the slide, the link to the documentation that try to put together all the informations that can be useful for the user, what I've said, plus many other details. And okay, you can go to the next slide. In particular, the data are released, let's say, in two kind of format. We release also the files are as basically they are used internally as they are, but these are in a format that is called frame format. And then we also have some sort of user-friendly data release, which is also provided another file format, which is called HDF5. And in this case, you can download the data directly by point and click in our website. You see in this slide a screenshot of the data page, in particular the one referring to O4A data release. You see that there are these orange yellow boxes that allow you to click and access to the data in two different sampling rates, so 4 kHz and 16 kHz. Then documents refer to the documentation I was just mentioning before, and timeline refer to what I will say in the next slide. So if you open one of these two pages, the archive pages, you will see a screen like you see in the middle here. So as you see, there is a list because we divide the data for the all run in small files, each containing 4096 seconds. And you see that there is a percentage that show you for which amount of time you have data in this almost 1 hour period of time, and you can download the files in this two format I was mentioning. And if, for example, you open one of the HDF5 files, you will see that it has the structure that you see in the last and the extreme right part of the the slides that has a collection of the metadata of the file, the quality which contains inside the bit mask with the details of the hardware injection and the data quality information, which is sampled at 1 kHz, and then the strain. And as you can see, the name of the file contains always the last digit, 4096 is the duration, and that this 10 digit before 1096 is the GPS time of the starting of that file. Okay, so I think that was it. So I will end to, no, sorry, I forgot. About the other important quantity is, I was mentioning the fact that the data are not always available. We have discussed about the fact that even during an observing run, the detectors are not always online. In addition, there could be some different data qualities categories, and you may want to have information about when hardware injection happened. And to do that, we use these tools that is called Timeline, which provide a view of the various segments available. You can have a view with like the one that is at the bottom of the slide, and you can get the start and stop of a duration of each segment as is showed in the right part of the slide. And also in this case, you see the time are given in GPS time, and the duration is in seconds. Okay, so now that's really all. So I end up to Matthew.
Okay. Just having a quick change of screen sharing. So I think that's showing now, Matthew. So over to you.
Hello, everybody. So I will present how you can access the catalog online, and also how you can access other types of data, like the one Agatha showed, and even more. So first of all, if you want to focus on the catalog, the GWTC 4.0 catalog, the main the gateway to access that is the event portal. So this is the screenshot of the GWOSC website. You can access the URL here. Those are links. You will have them. And starting from the event portal, you can access all the catalogs from GWTC 1, which was based on 01 and 02 runs, to the latest GWTC 4.0 catalog. You will also be able to access all the events that are in the catalogs, and even events that are not yet in the catalogs, and events that are for which the confidence is too low to be included in the catalogs. I will show you how to do that in the next slides. Just if you want to access the event portal, you need to click on the Get Data button here, and then on Events and Catalogs. You will then see this page, and the first button we'll explore is this one. Which will show you the catalog. So this is what you see when you click the button I just mentioned. So this is a table of events. Obviously, it's much longer. Oops, that's what can fit on the slides. Is the screen still sharing correctly? Yes. Okay. So this is here you would have the table of all the 219 events in the current GWTC 4.0 catalog. Remember, this is a cumulative catalog. That is, you will have the very first detection of gravitational waves up to the latest in the O4A run. If you click on such a link as this one, you will see it will bring you to the event, the details about the event page. So the event page for I pick up this example, which is one of the loudest events in the current catalog. So this page will show you all the details about this event, like its name, the GPS and the UTC time at which it happened, links to publication and so on. And it will also allow you to access the timeline. That is the last plot that Agatha showed that show you the state of the detector around the time of this event. Obviously, the page also here is much longer than what could fit on the slide. So you also have the links. You can take time to explore that. Also very important, you can download the strain files around this event. So you can reanalyze it if you want. And you also have access to the official results of the pipeline used by the LBK collaboration to find this event. That is the search pipelines, the various search pipelines, and the various parameter estimation pipelines. Last but not least, you also have plots. So those two are images of a typical representation of events that is used, which is called the Q transform plot. And if you click here, you can also you can access a web app that will allow you to manipulate those plots. Okay, so if we go back to our event portal, we explored what this button does. We now explore what this button does. So this button will bring you to a list of all the catalogs that are available. Once again, this is too long to fit on one slide. GWTC 4 is right here. You can see the very beginning of its description. So on the left, you have a link to a table of all the events of this catalog. And on the right, you have a short description which gives you links and documentation about the precise content of this catalog and links to publication and so on. So for instance, if you click here on GWTC, you will reach the same page that we've seen before with all the events of the current catalog. And you can also see here that the GWTC 1 was split into two different catalogs. You have the marginal catalog that contains events for which not all the criteria for confidence were met. So this is events that are those are not high confidence events. And the GWTC 1 confident catalog, which contains the confident events. Okay, so if we come back again to our event portal, we now explore what this button does. So this one will bring you to the list of all the events on the GOSC. You can see that it contains more events than the 219 of the GWTC 4.0 catalog. So this contains low confidence events and also events that, for instance, those three ones that are that happen during O4B, so the run after O4A, but which are interesting enough to be released earlier than the catalog. So those events will eventually be included into the next version of the catalog, GWTC 5. Okay. The last thing you can do to explore the catalogs is to use this button, which is the query button, which it will bring you to a query form that will allow you to search event by the name, the catalog they are in, the masses, and the different properties of the event, and also by time, the time at which it happens. So again, you will end up in a table of events from which you can reach the detailed event page about each event. So this is the way you can access the catalog online, explore it, find the events that interest you. And Agatha also showed that you can download the bulk, the strain in a user-friendly format from the website. One thing you might be interested to do is to access the data from a script, from a program. So there are several ways to do that, but one of the most useful is to use the package called GWPy, which allows you to access the gravitational waves data on the GWOSC website and also to process it. So to give you an example, this is a Python script that will download the data around the event we talked about, the GW23, 21, 26. No, sorry, 23, 12, 26, etc. So from this, this is to query the time at which the event occurred. We download 15 seconds of data before and after the event. These two lines, those two lines will download the data and will plot the strain data. And those three lines are used to download the data quality information and plot them into something resembling the timeline tool on the website. Okay, so with all of these, you're able to fetch the data and the properties of events you're manipulating. But as we told you, there are more data on more kind of data on the GWOSC website. As Agatha said, you can access the timeline and the user-friendly strain and quality data from the website. So you have interfaces from which you can query exactly at what time you're interested and download the files one by one. There are two different types of information that are also useful on the GWOSC website. The first one is so-called alternate strain data. So this is the strain data that Agatha mentioned. This is the data that is used by the LVK collaboration to produce the catalog. So you cannot download them directly from the website, but you can access them from GWPy using, again, only one line, one Python command to download them. I'm not going to explain what this means exactly. You will have to refer to the documentation about the alternate strain that is given on this page. And the second, well, the last kind of information that you can access on the GWOSC is the so-called auxiliary data. So Agatha talked about that. This is all the sensors that are used to track the state of the instrument and the environment. So this is used, for instance, to produce the data quality flags. Once again, you cannot download them directly, but you can use GWPy to fetch them on your computer, and then you can use them to define your own quality flags if you're interested into that. If you're a bit lost in all this information, remember that open science is not only open about data, but also about learning and tutorials. So the GWOSC maintains a catalog of tutorials and learning resources for gravitational wave. You have the links here. In particular, you can start with this tutorial that will show you how you can access the various types of information on the GWOSC. And if you want to go further, you can participate in open data workshop, which are organized by the GWOSC each year. And it's a 3 days crash course in gravitational wave data analysis. The next edition is to be announced soon. So stay tuned on that. You can also ask questions and on the forum, the gravitational wave community forum, where everybody is welcome and can ask any question. And just to give you a big challenge, from the GWOSC you can access a lot of data, really the data that is used to create the catalog. And since 2005, you can also publish your own catalog on the GWOSC website. So you can now download everything, create your own pipeline, and have your own catalog published on the GWAS website. That's it for me. I think it's time for the questions.
Many thanks, Matthew. Very much appreciated. So I think for questions, we're asking people to either type them into the chat or put their hand up, and we can, I believe, unmute you. So yeah, please, any questions folks have? I see a hand up from Shan Palmer. So please go ahead, Shan.
Hello.
Hi there.
Hi. My name is Shan, and I'm an undergrad from India. And I wanted to ask a question about the GWAS data pipelines, and specifically, I was wondering, like, how do independent softwares become associated with LIGO and are able to like uh, get documented on the website? Because I'm building something that's closely related, and I was wondering like what might be some steps to take it there.
Matthew, do you want to take that one?
Sorry, I was lost in all the buttons there. So if I understand your question, you're developing your own pipeline, so your own software to detect events and to estimate the parameters, right?
Actually, it's more of software that compiles all of the pipelines, so it is meant to remove the coding from the whole process of data analysis of gravitational waves. So it's like a GUI interactive software through which you
Okay.
can fetch the data, visualize it, run Omicron or other things.
Okay, so you use the existing tools for visualization and things like that, right?
Mm-hmm.
Okay.
Yeah.
So there is on the GWASC website a list of tutorials and software. In your case, it's mostly software. You can contact us and we can discuss the inclusion of your tool on this list. So it will be just we'll need a bit more information and discussion about exactly what this does,
Mhm.
and we can add it. You can find the contact address on the
Yeah,
website. So
got it. Yeah, thank you.
Okie doke. We did have a question in the Q&A, but Jonah has already answered it. Too quick. Other questions or hands up that folks have? Dish BJ? I think you can speak.
Hey, thanks for organizing this workshop. I had a question related to the one I posted on the Q&A. So, like, I mean, there is calibration and data cleaning done in the auxiliary data release files that I saw. So, but in the default files you mentioned, are there like these data calibration effects also like corrected for?
Agatha?
Yes. So yes. So we release the last. So as you have understood, we release data in many different ways. So what is called alternate strain contains all the different steps from with or without the cleaning and so on. But what is called the default data release, which the one that contain only one type of strain, that contain the last available calibration, the best possible cleaning and so. and so on. So if you are interested in different steps, you can check the alternate strain page that lists you all the different type of channels that you can get.
Okay, thanks a lot. And just to clarify, the default strain that was used for transient catalog detection by the pipelines, is that right?
Yes, I mean, so if you open the open data paper, you will see a table that is the number 4, which is the list of the exact name of the channel used internally that correspond to what you get with the typical fetch open data comment. So I'm looking down because I have it in my hand now, and I'm checking that is exactly the same channel name that Matthew is showing. So it's this. You cannot see it, but okay. If you download the open data paper, you see the list of exact name, channel name, and everything should be clear, hopefully.
And then to connect it to the searches in the methods paper for the transient searches, it then lists the specific channels that are used. And there is some pipeline dependency just because of the way that the pipelines are transitioning. So there is a plan to be consistent on it. The differences are very subtle. But yeah, there is currently still some discrepancies.
Okay, thanks a lot.
Okie doke. Any more questions? We have a minute or two left. I see one hand up from Sarah.
Hi, yes. I'm Sarah. I'm doing my PhD at University of Geneva, and I was working with, I think maybe it was proprietary gravitational waves data. I'm not exactly sure, but I think I have encountered like a naming issue or something like that. Could you maybe let us know if there is any inconsistencies in like metadata of published catalogs? I am specifically wondering about, maybe I can send it in the Q&A chat.
You sure can.
Yeah, I think so. Maybe this is something that I have been, the link that I have been using, and maybe there is a chance that I have downloaded it wrong, but also I kind of sense that it's something wrong with the data.
Jonah's got his hand up. So Jonah, do you want to?
Yeah, Sarah, I'd love to help you with this issue. This seems a little bit more than technical than we can handle right here on a webinar. We have a couple of ways to get in touch that we should advertise. So the best is ask.igwin.org. And if you can write some notes about exactly the issue you're seeing and post them there, that would be a great way for us to take a look at it. And if all else fails, you can always email us. We do advertise an email address from the GWASC homepage.
Okay, sure. Thank you very much.
Okay, I'll look forward to hearing from you. Thanks for your interest.
Yep.
So I've dropped a link into the answer to Sarah's question at ask.igwin. Okay, then I think with that we can close up the call. Thank you everyone for joining. We really appreciate your time and we're really excited to share this with you. Please do keep your eyes out for the next set of webinars. So they'll be coming up and advertised, and they'll cover the methods and results, and then moving on to the astrophysics that we can do with this exciting new data. And of course, we have more data in the pipeline that's coming. So please, keep your eyes on this space. And I guess let me reiterate what Jonah sort of said at the end there. If there are any questions that come up, then ask.igwin.org is, I guess, the first port of call. And you can also email folks as well. With that, then I'll close up and thank everyone for joining. And thank you to all of the panelists. I think a really nice job, and take care. See you all sometime soon.